Hi folks, welcome to the concavity recap. Concavity refers to sort of the spooniness of a function, so which direction the spoon would be facing. If something is concave down, like it is over this interval, then it's a spoon that would not hold soup, or concave down. If, on the other hand, it's a spoon that's facing upwards that would hold soup, then it's concave up. Now it's the second derivative that tells us about concavity. So if the second derivative is positive, like this, then we're talking about concave up. If the second derivative is negative, then we're talking about concave down. And the place where concavity changes, that's a point of inflection. Here are the steps for determining concavity and points of inflection. So first of all, we'll find the critical values on the second derivative. Then we'll make a sign diagram for the second derivative to determine the concavity on the original function. And lastly, whenever concavity changes, we've found a point of inflection, assuming that the original function actually exists at that point. So if we took a look at this cubic here of x cubed minus 6x squared plus 3, we can differentiate it. We get 3x squared minus 12x. We can differentiate again. There's our second derivative. That's what we really care about. I need to find the critical values on that second derivative. So I can either make y double prime 0 and actually solve the equation, or do a little bit of factorization, or maybe just by inspection be able to tell that the critical value is 2. Now I'm ready to test on that number line. So here's my critical value of 2. I've got y double prime. If I put in a number that's less than 2 into the second derivative, in any of its forms, I'm going to get a negative value. So if I put in 0 into the second derivative, I'd get negative 12. That means to start with, the function is concave down. If I put a number bigger than 2 into the second derivative, I'll get a positive value. You can see that here. And that means it goes concave up. In other words, what's happening around 2 is it's going from concave down to concave up. This is going to be our point of inflection that we found. It's at an x value of 2, and to find its corresponding y, I just throw it into the original function over here, and I'll get negative 13. If I want to list the intervals of concave up and concave down, it's concave down all the way until x is 2. So in interval notation, that's from negative infinity to 2. It's concave up everywhere after 2. So in interval notation, that's from 2 until infinity. Let's take a look on Desmos. There's our function. You can see it's starting off concave down. And then somewhere around here, it's changing to concave up. And it seems reasonable that it's about here at 2. And now it's concave up forevermore. The last thing we looked at in our concavity section was this second derivative test for a max or min. Now to be clear, the second derivative test for a max or min also involves the first derivative. You've got to find points where you have a first derivative of 0, which means that you're horizontal. Once you've established that you're horizontal at a given x value, then you check the concavity. If it turns out that your second derivative is positive at that point, then you're concave up, which looks like this, and automatically you must have found a minimum. If, on the other hand, your second derivative turns out to be negative, then that means that you're concave down, which looks like this, and that must mean you found a maximum. It's not really worth memorizing rules around up and down and max and min. As long as you can sketch it, you should be fine. So here's an example. Suppose g of x is a function that's smooth and continuous everywhere. It's known that g prime at negative 1 is 0, and g double prime at negative 1 is 5. What do we know about the original function g of x at x equals negative 1? Well, here are the things that we've been told. G prime at negative 1 is 0. In other words, g of x is horizontal at x equals negative 1. We've also been told that g double prime at -1 is 5. That's a positive value right here. So g of x must be concave up at this point. If we were to draw that, let's see, it's horizontal and concave up. Must be a point like this, or it's drawn a little better down here. Clearly, we've got a minimum at x equals -1. Those are the big ideas in the section. Mostly it boils down to the fact that the second derivative controls concavity, and concavity can find points of inflection directly, and it can also help us suss out whether horizontal spots represent maxima or minima.